Okay, inside the plasma, if we just look at a surface, if you insert a piece of paper and measure the electron flux and ion flux, right, across the surface of paper, you will find out inside the plasma body, the electron flux is much larger than ion flux. But in sheath region, in any sheath, right, ground sheath, floating sheath, cathode sheath, and anode sheath, in all the sheath regions, we can find out both the flux of electron and flux of ions change. And in a steady state, steady plasma, one can find out eventually electron flux and ion flux are equal. Electron flux and ion flux are equal, okay? And this is the basic diffusion equation, right, based on Fick's first law. The flux depends on the concentration gradient, right? And here's a proportional coefficient, which is named diffusion coefficient. So this is a fundamental of the Fick's first law. Fick's first law, okay? And actually, you should place a minus sign for the Fick's first law, right? So J is the flux, J sub E is flux of electron, and J sub I is the flux of ion. And D is the diffusion coefficient. So inside the plasma body, the diffusion coefficient for electron is much larger than the diffusion coefficient of ion. Okay, and in the sheath region, if we look at the last slide, we can find out in the pre-sheath region, the density of electron decrease when we look at the region close to the cathode surface. And the density of ion also decrease. And if we calculate the gradient, right, we need to get a delta N divided by delta X, right? Delta N divided by delta X. So at the same place from this figure in the pre-sheath region, the ion and the electron has the same gradient, same concentration gradient in the pre-sheath region. Okay. So first, the concentration gradient are about equal. Concentration gradient about equal. dNE dx and dNi dx. And at steady state condition, when we look at the surface of the cathode or surface of a floating substrate, the surface collect same flux of electron and ion. So it means even there is a floating surface, once it reach a steady state, the charge is negative, right? The surface is charged negatively, but the charge will not keep building up. Okay. So for a certain period of time, if we calculate the number of electrons collected and the number of ions collected, they are equal in the steady state. Okay. So it means the flux of electron and flux of ions are equal. And based on this equation, the diffusion coefficient for electrons and ions in the sheath region are also equal. But inside plasma body, the diffusion coefficient for electron is higher than diffusion coefficient of ion. But in the Schiff region, the diffusion coefficient of ion and electrons are equal. And this kind of phenomenon is named M-bipolar diffusion, right? Bipolar, negative charge and positive charge, bipolar, okay? So for both type of particles, they are lost to the floating surface, or lost to a ground chamber wall, or lost to a cathode or anode. Right? They have the same loss rate because the flux are equal, and the diffusion the bipolar diffusion coefficient is about the diffusion coefficient of ion times on the bracket 1 plus electron temperature divided by ion temperature. Okay, so one can get a diffusion coefficient in the Schiff region. Okay, so of course the collective phenomena of bipolar diffusion, this behavior, okay, cause electrons and ions travel with the same diffusion coefficient, which is labeled as D sub A. Okay, so this is the second collective phenomena. So in the Schiff, electron and ions have the same flux, and they lost to chamber wall, or they lost to the ground surface or the cathode surface at the same rates. And the third collective phenomena is the plasma oscillation. Plasma oscillation. Okay, so so at the beginning we can consider in the plasma body, right? There are equal numbers of the electrons and ions, and ions and electrons are uniformly distributed inside the plasma body. And if we try to if we calculate the center of positive charge and the center of negative charge, they should be at the same place. So they coincide at the same place. So at the beginning, ions and electrons has the same distribution, uniform distribution inside plasma body. Okay. But if the plasma, if we apply, or if there's just some reason that inside the plasma there is a disturbance of electrical field, right? So the small electrical field will cause electrons and ions, right, move toward opposite direction. So if there is an electrical field, right, pointing from left side to the right side along this direction, along this electric field along this direction, okay, and then we can find out. Okay, so this should be a reverse. Okay, if the electrical field point along this direction, then ion should move toward right, and the electron should move toward the left side. So before the plasma experience the electrical field, the center of positive charge and the center of negative charge should coincide there. But if there is an instantaneous electrical field applied to the plasma, then all of a sudden the ions will move toward this direction, and the electron move toward the opposite direction. But once they shift along this direction, there is plasma oscillation. And plasma oscillation can be analyzed and by represented by this equation. So here the zeta is the displacement of the charge. So the displacement of the charge is a function of time. Right? So the negative charge will move back and forth, back and forth, back and forth like this way. Okay, and ions also travel back and forth, back and forth. So the amount of displacement zeta is a function of time. Function of time. Okay, and this oscillation can be described by this differential equation. Differential equation, and here omega here is the angular frequency of plasma, of the electron inside the plasma. Okay, and by analyzing this equation, you can get the angular frequency of electron inside the plasma is the square root of the square of charge times density of electron divided by the vacuum permittivity and the mass of electron. Mass of electron, okay? And these three, right? The charge, vacuum permittivity, and the mass of electrons are constant. So right here, only the N0 electron density, only the electron density is a factor, right? So the electron oscillation frequency or electron plasma frequency depends on the square root of N0, square root of electron density. So if you have a high density electron, it means you have high density plasma. It means you have high density electron, and then the oscillation frequency will be high. If you have a low density plasma, then the oscillation frequency is small, okay? And the displacement of the charges, right, as a function of time can be represented by a cosine function. It moves back and forth, okay? And omega is the angular frequency. And if we just calculate the frequency, we can divide by angular frequency divided by 2 pi, okay? And this frequency is what we always get in many applications, okay? So the frequency of electron plasma frequency is about 8,980 times square root of electron density. And the electron density is represented by number per cube centimeter. Okay? And the frequency is in a unit of hertz. Okay? And if we no, not this one, okay. If we check the previous slide, we can find out in this figure, we can find out the plasma we are interested, right, is in this region, glow discharge, right? We can generate plasma in lab, and this type of plasma is usually belongs to the glow discharge. And from this figure, we can find out the density, electron density or plasma density, right, is about 10 to 10 10 to 10, or higher, 10 to 12. Okay, from maybe 10 to 9 to 10 to 12 per cube centimeter. Per cube centimeter, okay. This is the plasma we can get. A little bit low density plasma or high density plasma. So if you generate a plasma with electron density of 10 to 12 per cube centimeter, right? And then you can find out the plasma frequency is 8,980 times 10 to 6, right? So you got a frequency So you got an electron plasma frequency of 8.98 times 10 to 9 hertz. 10 to 9 hertz is gigahertz. So you can generate, when you generate plasma, the plasma, electron plasma frequency is around a few gigahertz. So it depends on the electron density. And usually the plasma we generated can deliver a plasma electron plasma frequency between 1 to 10 gigahertz. And this kind of the oscillation will generate electromagnetic wave. Right? So the frequency, right, is following the range of the communication frequency. Right? Right now we use the cellular phone or mobile phone with the communication frequency of 1.8 gigahertz, right? 1.8 gigahertz. Or if you have lately a model of the cellular phone, you might use the frequency of 2.45 gigahertz. And in the earlier version, we can use the 900 megahertz, equals 0.9 gigahertz. So these frequencies are used for communication, right? Electromagnetic wave used for communication. And the frequency of 2.45 gigahertz is also used for microwave oven. Okay. So actually, when you generate a plasma with such electron density, you also generate an electromagnetic wave flowing this region. Okay. So sometimes when we set up a plasma system, we need to think about the plasma oscillation, because the plasma will radiate the high frequency electromagnetic wave. And this electromagnetic wave will interfere communication. And this also interfere the control panel, the electronics control panel. Okay. So there are several things we have to know about before we build up a plasma system. So first thing, you have to block this electromagnetic wave. And the second thing, you need to use a special window to block UV radiation. or you need to wear a UV protective goggle to look at the plasma. Okay. And if you generate plasma with a lower density, and then the plasma oscillation frequency fall to RF region, radio frequency, RF. So in the radio frequency the region, the electromagnetic wave was used for broadcast for radios, and the communication for the airplanes. Okay, so you have to know about this. Okay. So this equation gives us the electron plasma frequency. And inside the plasma, electron oscillate. Ions also oscillate. Right? But the ion oscillate with a smaller frequency than electron, because the mass of ion is much larger than the mass of electron. So ion oscillate at smaller frequency, And the total frequency of plasma is the natural frequency. So it's the square of electron frequency, oscillation frequency, plus square of the ion oscillation frequency, and then take a square root. So this is the natural frequency of plasma. Okay. So from this slide, we know once we generate plasma, the plasma will irradiate the electromagnetic wave, right? Because the electrons and ions oscillate. But if you think of this story in another way, if you apply an electromagnetic wave with the frequency in this region, you can cause the electrons and ions to oscillate. And the plasma can be generated easily if you apply the microwave. You can use a simple microwave setup to generate plasma, right? Because the frequency is close to the oscillation frequency of plasma. Okay, so there are three collective phenomena, like plasma shifts and bipolar diffusion, and the oscillation and the plasma frequency. Okay. And then we move to another topic. So this is the voltage and the current relationship in a glow discharge or in a plasma generated by electrical field. Okay. And this figure shows a simplified circuit and the schematic of the plasma system. Right, this figure. So you can get a quartz tube, and place cathode and anode at the two ends. So this experiment was done by Crook, and later on several scientists. Okay, one of the famous scientists is Thomson. Okay, so here is the quartz tube, and you can fill in the gas and control the gas pressure, and then apply the DC bias, so that the gas between cathode and anode become ionized and reach a discharge condition or a plasma condition. Okay, so between cathode and anode there is plasma, and the electron and the ions inside the plasma can conduct electricity. So here forms a closed circuit. This part forms a closed circuit. So plasma is considered as a component in a circuit. Okay, and then we can put a voltmeter, right? Voltmeter in the parallel circuit, and put an ammeter. Somewhere put an ammeter in series of the circuit, so that you can measure the voltage and the current in this circuit, and then find out the voltage and the current, and plot the IV curve or VI curve, and find out from the low current or low current density to high current density, the discharge voltage change like this way. And then there are several regions. And here is a dash line. Right? On the right side of the dash line, one labeled breakdown. So the breakdown means the gas change from insulating condition to a conducting condition. Breakdown. Okay. Automatically, if you just apply a bias voltage, the gas will be ionized. So the breakdown condition. So if inside the tube, the plasma, right? Once you generate it, the plasma can cause a current flowing through, but the current, if the current is very small, right, 10 to minus 11, 10 to minus 12 amp, with such low current, the plasma will be unstable. They cannot be stable. Right, so once you apply a high voltage between the cathode and anode, you might get burst of plasma. So the plasma will generate it and then extinguish. So plasma cannot last continuously. Okay. So in order to get stable discharge with low current, right, in a low current region, you need another source to assist discharge. Another source. Okay, you cannot just use one set of DC power supply. Okay, so below this line, if the current is very small, you cannot get stable plasma. But if you generate plasma and with a current higher than maybe a 10 to minus 10 amp, you start getting a continuous stable plasma. And this part is called self-sustained plasma or self-sustained current. It means you can just use one DC power supply to generate a stable plasma. Okay, but the criterion is that the current must be higher than 10 to minus 10 amp. Okay, and Thomson analyzed the condition for the self-sustaining region. Okay, so later on in this chapter, where we can see Thomson analyzed the plasma condition and find out a few important factors. So actually there are two important factors. One is the ionization energy of the gas, ionization energy. And the other one is the property of cathode surface. Property of cathode surface. Okay. Now later on we can see tungsten, the analysis of the glow discharge by tungsten. Okay. So once the condition satisfies the tungsten criterion, the discharge will change the stable region. So in the stable discharge region, we can see there are several regions. Right? In this region is corona discharge. So the current density is about 10 to minus 5 amp per centimeter square. Or if you use the electrode with the area of 1 centimeter, you can just consider the current is around 10 to minus 5 amp. It's 10 microamp. Okay. And if you keep increase the current, you can find out the voltage, right? The applied voltage required to generate plasma, right? The applied voltage start decreasing, and then fall to this region. And in this region, the current from 10 to minus 4 amp to about 10 to minus 1 amp. This region belongs to the glow discharge. Glow discharge, okay. And in our class, right, one chapter, there's one chapter of the sputtering and one chapter of the plasma enhanced chemical vapor deposition. So the sputtering requires high energy ions, right? Then ions gain energy from cathode sheaths. So we need a high voltage, high applied voltage. And from this figure, we can see in this region, abnormal glow. If you increase current a little bit, the voltage will increase a lot. Okay, so this part is called abnormal glow, and we use abnormal glow to run sputtering process. And for the plasma enhanced chemical vapor deposition process, usually people control their plasma condition in normal glow. So in the normal glow region, if you increase the current, right, from 10 to minus 3 amp to about 10 to minus 2 amp, in this region, when you change the current, the potential between cathode and anode remain almost the same. Then this part is called normal glow. So in industry, people use normal glow to run plasma enhanced chemical vapor deposition. And if we compare the voltage in normal glow and abnormal glow, right, for the normal glow, the voltage might be around few hundred volts. And for the abnormal glow, the voltage can increase to few hundred and almost 1,000 volts. 1,000 volts. Okay. So it depends on the gas and the cathode material you use. The voltage will change a little bit. Okay. So this figure tells us there are several kinds of plasma. Right? Depends on the current density. So we can use corona, we can use normal glow and abnormal glow for most materials processing. Right? You can generate corona in air, just at 1 atmospheric pressure, corona. Right? So that the corona in air will generate ozone. And ozone can be used for different purposes. Right? And if you use normal glow, you can run plasma-enhanced chemical vapor deposition and abnormal growth for sputtering and sputter deposition. Okay, and this part is also important. Arc. So if you keep increasing the current, right? So from abnormal glow region, when you increase current, the voltage will increase. And then all of a sudden, if the condition across this line, then you will find out the voltage will drop a lot, drop to only a few tenths of volt. But the current density will increase a lot. And then the plasma become arc. They will become an arc. So arc just look like the this way, arc. Arc is a very localized discharge. Even though you might use an electrode with an area of 10 or diameter of 10 centimeter, once the arc is generated, you will find out the diameter of arc might be only 1 millimeter. Arc. Okay. So arc is characterized with high current density and low voltage. High current density and low voltage. And in industry, people use arc to melt metal or to weld metal pieces. Okay, because those concentrated arc can bring a large amount of heat. Okay, so there are several regions. Okay. Okay. So any question about the IV curves of the closed discharge? Next few slides, I will explain the breakdown, electrical breakdown. Okay, and this part is analyzed by Thomson and the scientists, other scientists. Okay, so this figure shows if we generate a DC plasma, right, the gas molecule or gas atoms between cathode and anode might be ionized. Okay. So once they are cations and the electrons, the cation will travel toward the negative cathode. The electrons will travel toward the positive anode. Okay. So they travel in opposite directions. Okay. This is the basic analysis. Okay, but at the beginning, right, most gas atoms or gas molecules are neutral. They are neutral, right, between cathode and anode. So if we want to generate plasma, we need a process, right? Electron impact ionization. So you need to gain electron with high energy. But how can electron gain high energy? Right. Electrons will travel along the opposite direction of electrical field. So once you apply apply voltage between cathode and anode, you can generate an electrical field. So in this case, the electrical field will point toward the right side. Electron will travel along this direction and pointing toward the left side. And when electrons travel, they gain energy. They gain energy because the force the force, right, applied on the electron equals to the charge of electron times electrical field, right? And the force will accelerate the electron based on Newton's equation. Equals to the mass of electron times the acceleration. So if the electron travel for a period of time, the electron will gain such amount of energy. So you can calculate. So if the first electron came out from cathode surface, when it traveled all the way to the anode surface, if there is no collision, there's no collisional process, we can calculate the energy of electrons gained from electrical field. All right. So the energy of electron gained from electrical field equals to the charge, the energy equal to the charge of electron times the applied voltage. Applied voltage between these two. Okay, the total energy gain. But if electrons travel for a short distance, they gain only small amount of energy. Only small amount of energy. So depends on the location of the electron, their energy will change inside the electrical field. Okay. So once the energy of electron is high enough, when they're traveling, when they collide with neutral gas atom, they got the chance to ionize the gas by electron impact ionization. So Thomson analyze the discharge and find out the condition to get sustain the plasma, okay? And then let's come back to this place where the first electron from. Right. At the beginning, we can assume all the gases are in neutral state. All the gases are in neutral state. So if we apply an electrical field between cathode and anode, right, nothing will be affected at the beginning, right? If there is no electrons or there is no ions, okay? But there are cosmic rays, right, coming from the universe, and these cosmic rays can create electron and ion pairs in air. Okay, so thanks to the nature. Right. They are cosmic rays come to close to the surface of the Earth. So these cosmic rays can generate electron and ion pairs in air with such 20 ions per cube centimeter per second in air. Okay. So these cosmic rays can generate electron and ion pairs. So actually, at the beginning, inside the quartz tube, there are very small amount of electrons and ions. So once they are electrons and ions, they will be accelerated by electrical field, so that electron can gain energy. Right. So this is the first part. Okay, and they are one need a multiple collisional process to generate more electron and ion pairs. So before the first electron travel from cathode surface to the anode surface, right? There must be a new electron and ion pairs generated. Otherwise, when the electrons come to the anode surface, the electron will be collected by anode. And then in the plasma body, the number of electrons will decrease. So in order to keep the plasma, right, in a discharge condition, before the electron is lost to the anode surface, the system must generate one electron, at least one electron. Okay, so the Thomson analyzed this kind of criterion. Okay, so in this part, the first important thing is that in the discharge tube, when the electron travel for distance d, certain distance, the energy of the electron increased by the electrical field. Okay, so if the electron travels for a longer distance, the energy of the electron will be higher. Longer distance energy of the electron will be higher. So when electrons collide with neutral atoms, right? So the high energy electron collide with neutral atoms, they can generate electron and ion pairs. So if the electron travel for longer distance, the opportunity of the electron impact ionization will also increase. So in this assumption, if we start from the cathode surface, right, and here is the x axis, and here is 0. Okay, so if the electron travel for up to this place for distance d or delta x, right? We can calculate the number of electron and ion pairs as a function of the distance. Okay, so okay, so here is the analysis. So if at the beginning, right, there are n sub x electrons, right, moving with a thickness of dx, and then the newly generated electron and ion pairs dn equals to nx dx and times an alpha coefficient, alpha parameter, and this alpha parameter is related to the ionization energy and the electrical field. Okay, so dn equal to alpha nx dx, and if you integrate the left side and the right side from x equals to 0 to x equals to the d is the distance between cathode and anode. Okay, so at the beginning there are n e sub 0 of the electron density right? And at the anode surface, the electron density will change to n sub e, following this equation. Okay.